National Electrical Code Section 250.119 stipulates that grounded conductors in an alternating current system must be either white or grey. For direct current systems, the grounded conductor must be white with a negative polarity or green with a positive polarity. The primary reason for this regulation is to enable personnel working on electrical systems to readily identify grounded conductors, thereby enhancing safety and preventing potential hazards. In this particular scenario, the initial design of the system incorporated a secondary power supply operating at 240 volts, which was intentionally left ungrounded. However, at some point after the system was installed, one leg of the 240 volt secondary was grounded. This modification introduced a discrepancy because the conductors that were subsequently grounded were not color-coded appropriately to indicate their new function. Specifically, these conductors remain black, which is the standard color for ungrounded conductors. As a result, there is a risk of misidentification, which could lead to unsafe practices when working on the system. Therefore, it is necessary to take corrective action to ensure that the grounded conductors are properly identified. The recommended approach is to either replace the existing black conductors with white or grey conductors, or to mark them with white tape or another suitable marking method to clearly indicate that they are grounded. According to the National Electrical Code, it is not mandatory to replace the conductors entirely as long as they are properly marked to indicate their grounded status. This approach aligns with the code's intent to ensure that grounded conductors are easily identifiable for safety purposes. When incorporating additional servo drives into the system, it is crucial to ensure that all newly installed grounded conductors are ordered in white. This proactive measure will help maintain consistency and prevent any confusion regarding the identification of grounded conductors in the future. The National Electrical Code provides specific guidelines for identifying grounded conductors. Section 200.6 of the National Electrical Code addresses the use of specifically the color white or grey for the identification of the grounded conductor. This section details the requirements for insulated grounded conductors in sizes 6 American wire gauge or smaller, specifying that they must have an outer finish that is continuously white or grey. This continuous marking ensures that the conductor is easily identifiable throughout its entire length. For conductors larger than 6 American wire gauge, the National Electrical Code permits the use of white or grey marking at the time of installation. This marking can be in the form of tape, painting, or other effective means applied at the termination points and at each location where the conductor is accessible. This allows for flexibility in identifying larger conductors while still maintaining the essential requirement of clear identification. The purpose of these color coding requirements is to prevent accidental contact with energized parts and to reduce the risk of electrical shock. By consistently using white or grey for grounded conductors, electricians and other personnel can quickly and accurately identify the neutral or grounded conductor in a circuit. This is particularly important in complex electrical systems where multiple conductors are present. The requirements for grounded conductor identification also extend to specific applications such as flexible cores and fixture wires. These conductors must also be identified by a white or grey color. In summary, the National Electrical Code mandates the use of white or grey color coding for grounded conductors to ensure safety and prevent electrical accidents. The code provides specific guidelines for conductors of different sizes and applications, allowing for both continuous marking and marking at the time of installation. These requirements are essential for maintaining a safe and reliable electrical system. Grounding and bonding are critical components of electrical safety. Grounding is the process of connecting electrical circuits and equipment to the earth, while bonding involves connecting non-current carrying metal parts of an electrical system together to create a low-impedance path for fault current. These practices are essential for preventing electrical shock, minimizing the risk of fire, and ensuring the proper operation of electrical equipment. The National Electrical Code outlines specific requirements for grounding and bonding to ensure that electrical systems are installed and maintained safely. Grounding is essential for providing a path for fault current to flow back to the source, which allows overcurrent protection devices, such as circuit breakers and fuses, to quickly trip and de-energize the circuit. This rapid response minimizes the duration of a fault, reducing the risk of electrical shock and fire. The grounding system typically consists of a grounding electrode, such as a ground rod or a metal water pipe, which is connected to the electrical system through a grounding conductor. The grounding conductor must be sized appropriately to handle the maximum fault current that could occur in the system. Bonding is equally important for creating a low impedance path for fault current. When non-current carrying metal parts of an electrical system are bonded together, they provide a continuous path for fault current to flow back to the source. This ensures that all metal parts are at the same electrical potential, reducing the risk of electrical shock if a person comes into contact with a faulted metal part. Bonding is typically achieved by using bonding jumpers, which are conductors that connect metal parts together. The National Electrical Code provides detailed requirements for bonding various components of an electrical system, including metal conduits, enclosures, and equipment frames. The size of the bonding jumpers must be adequate to handle the maximum fault current that could occur in the system. Effective grounding and bonding are essential for protecting people and property from electrical hazards. By providing a low impedance path for fault current, grounding and bonding ensure that overcurrent protection devices can quickly de-energize a faulted circuit, minimizing the risk of electrical shock and fire. The National Electrical Code provides comprehensive requirements for grounding and bonding, which must be followed to ensure the safety of electrical systems. In addition to the general requirements for grounding and bonding, the National Electrical Code also includes specific requirements for different types of electrical systems and equipment. For example, there are specific requirements for grounding and bonding in healthcare facilities, industrial plants, and agricultural buildings. These requirements take into account the unique hazards that are present in these environments. Healthcare facilities, for instance, have stringent requirements for grounding and bonding to protect patients and medical personnel from electrical shock. These requirements include the use of isolated power systems and equipotential grounding to minimize the risk of leakage current. Industrial plants often have large electrical systems with heavy equipment, which can generate significant fault currents. The grounding and bonding systems in these facilities must be designed to handle these high fault currents and protect workers from electrical hazards. Agricultural buildings, such as barns and poultry houses, can be particularly susceptible to electrical problems due to the presence of moisture, dust, and corrosive materials. The National Electrical Code includes specific requirements for grounding and bonding in these buildings to minimize the risk of electrical shock and fire. Understanding the specific requirements for grounding and bonding in different types of electrical systems is essential for ensuring the safety of people and property. The National Electrical Code provides a comprehensive set of guidelines for grounding and bonding, which must be followed to ensure that electrical systems are installed and maintained safely. Overcurrent protection is a critical aspect of electrical safety, designed to protect electrical circuits and equipment from excessive current flow. Overcurrent can result from various causes, including short circuits, ground faults, and overloads. Without proper overcurrent protection, these conditions can lead to overheating, damage to equipment, and even electrical fires. Overcurrent protection devices, such as circuit breakers and fuses, are designed to automatically interrupt the flow of current when it exceeds a predetermined level. These devices are essential for preventing electrical hazards and ensuring the safe operation of electrical systems. Circuit breakers are electromechanical devices that trip and open a circuit when an overcurrent condition is detected. They can be reset manually after the fault has been cleared, making them reusable. Fuses, on the other hand, are single-use devices that melt and break the circuit when an overcurrent condition occurs. Fuses must be replaced after they have been blown. The selection of the appropriate overcurrent protection device depends on the specific application and the characteristics of the electrical circuit. Factors to consider include the voltage and current rating of the circuit, the type of load being served, and the potential for fault current. The National Electrical Code provides detailed guidelines for selecting and installing overcurrent protection devices to ensure that they provide adequate protection for electrical circuits and equipment. Short circuits are a common cause of overcurrent. A short circuit occurs when there is an unintended low resistance path between two conductors in a circuit. This can happen when insulation fails or when conductors come into contact with each other. When a short circuit occurs, the current flow increases dramatically, potentially causing severe damage to equipment and creating a fire hazard. Overcurrent protection devices are designed to quickly interrupt the flow of current during a short circuit, preventing these hazards. Ground faults are another type of overcurrent condition. A ground fault occurs when a current-carrying conductor comes into contact with a grounded metal part of an electrical system. This can happen when insulation fails or where equipment is damaged. When a ground fault occurs, the current flows through the grounding system, which can create a shock hazard if the grounding system is not properly installed or maintained. Ground fault circuit interrupters are special types of overcurrent protection devices that are designed to detect ground faults and quickly interrupt the flow of current. GFCIs are required in many locations such as bathrooms, kitchens, and outdoor areas to protect people from electrical shock. Overloads are a third type of overcurrent condition. An overload occurs when a circuit is subjected to a current flow that exceeds its rated capacity. This can happen when too many devices are plugged into a circuit or when equipment is operated beyond its design limits. Overloads can cause overheating of conductors and equipment, which can lead to insulation damage, reduced equipment life, and even electrical fires. Overcurrent protection devices are designed to protect circuits from overloads by interrupting the flow of current before it reaches a dangerous level. The National Electrical Code provides specific requirements for overcurrent protection to ensure that electrical systems are protected from short circuits, ground faults, and overloads. These requirements are essential for preventing electrical hazards and ensuring the safe operation of electrical equipment. In addition to the requirements for overcurrent protection, the National Electrical Code also includes requirements for conductor sizing and insulation. Conductor sizing is the process of selecting the appropriate size of electrical conductors to carry the intended current without overheating. The size of the conductors must be adequate to handle the maximum current that could flow in the circuit, taking into account factors such as the ambient temperature and the number of conductors in a raceway. The National Electrical Code provides tables and formulas for determining the appropriate conductor size for various applications. Insulation is the material that surrounds electrical conductors to prevent them from coming into contact with each other or with grounded metal parts. The insulation must be rated for the voltage and temperature of the circuit, and it must be resistant to moisture, chemicals, and other environmental factors. The National Electrical Code specifies the types of insulation that are suitable for different applications. Proper conductor sizing and insulation are essential for preventing electrical hazards and ensuring the reliable operation of electrical systems. Undersized conductors can overheat, leading to insulation damage and potentially causing electrical fires. Damaged or inadequate insulation can create short circuits or ground faults, which can result in electrical shock or equipment damage. The National Electrical Code provides comprehensive requirements for conductor sizing and insulation to ensure that electrical systems are installed and maintained safely. Electrical enclosures are protective housings that enclose electrical components and equipment. Enclosures provide physical protection for the enclosed components, preventing them from being damaged by environmental factors such as moisture, dust, and chemicals. Enclosures also provide electrical safety, protecting people from contact with energized parts. The National Electrical Code specifies the types of enclosures that are suitable for different applications, taking into account the environmental conditions and the potential for electrical hazards. Enclosures are typically made of metal or non-metallic materials. Metal enclosures provide excellent mechanical protection and can also provide electromagnetic shielding. Non-metallic enclosures are lightweight and resistant to corrosion, making them suitable for use in harsh environments. The type of enclosure required depends on the specific application. For example, enclosures used in wet locations must be watertight to prevent moisture from entering and damaging the enclosed components. Enclosures used in hazardous locations must be explosion-proof to prevent explosions from occurring inside the enclosure. The National Electrical Code provides detailed requirements for electrical enclosures to ensure that they provide adequate protection for electrical components and equipment. These requirements are essential for preventing electrical hazards and ensuring the reliable operation of electrical systems. Wiring methods refer to the techniques and materials used to install electrical conductors and equipment. The National Electrical Code specifies the approved wiring methods for different applications, taking into account factors such as the type of building, the environmental conditions, and the potential for electrical hazards. Common wiring methods include conduit cable and wireways. Conduit is a rigid or flexible tube used to protect electrical conductors. Conduit can be made of metal or non-metallic materials, and it provides excellent mechanical protection for the enclosed conductors. Cable is a factory assembly of two or more insulated conductors enclosed in a protector sheath. Cable is easier to install than conduit, but it does not provide as much mechanical protection. Wireways are metal or non-metallic troughs used to support and protect electrical conductors. Wireways are typically used in industrial and commercial applications where there are a large number of conductors. The National Electrical Code provides detailed requirements for wiring methods to ensure that electrical conductors and equipment are installed safely and reliably. These requirements are essential for preventing electrical hazards and ensuring the proper operation of electrical systems. Electrical safety is a critical concern for anyone working with or around electrical systems. Electricity can be dangerous, and it is essential to take precautions to prevent electrical shock, burns, and other injuries. The National Electrical Code provides comprehensive guidelines for electrical safety, covering topics such as grounding, bonding, overcurrent protection, conductor sizing, insulation, enclosures, and wiring methods. Following these guidelines is essential for ensuring the safety of people and property. One of the most important aspects of electrical safety is to always de-energize circuits before working on them. This means turning off the power at the source, such as a circuit breaker or a disconnect switch. It is also important to verify that the circuit is de-energized using a voltage tester before touching any conductors or equipment. Another important safety precaution is to use appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools. These items can help protect you from electrical shock and burns. It is also important to be aware of the potential hazards in your work environment. Look for exposed conductors, damaged insulation, and other potential safety hazards. Report any hazards to your supervisor or take steps to correct them yourself. Electrical safety is a shared responsibility. Everyone who works with or around electrical systems has a responsibility to follow safety guidelines and take precautions to prevent accidents. By following these guidelines, you can help ensure the safety of yourself and others. The information provided here is intended for general guidance only and should not be considered a substitute for professional electrical training or advice. Always consult with a qualified electrician or electrical engineer before working on any electrical system. Additionally, always refer to the latest edition of the National Electrical Code for specific requirements and guidelines. Ignoring electrical safety can have serious consequences, including electrical shock, burns, fires, and even death. Taking the time to learn about electrical safety and following safety guidelines can help prevent these tragedies and ensure a safe working environment. Remember, electricity is a powerful force that must be treated with respect. By following the principles of electrical safety, you can work safely and prevent accidents. In conclusion, ensuring the correct identification and maintenance of grounded conductors is paramount for electrical safety. Adhering to the National Electrical Code guidelines, particularly those outlined in Section 250.119 and related sections on grounding, bonding, and overcurrent protection, is essential. Whether it involves replacing incorrectly colored conductors or properly marking them with white tape, these actions contribute significantly to preventing electrical hazards. Furthermore, understanding and implementing proper wiring methods, utilizing appropriate enclosures, and consistently practicing electrical safety protocols are all integral components of a comprehensive approach to electrical safety. By prioritizing these measures, both individuals working directly with electrical systems and those in the surrounding environment can be better protected from potential risks, ensuring a safer and more reliable electrical infrastructure.